Electronic Solution. This session is all about embedded system and application development. I'll be going through like what is an embedded system, what are the main design challenges that are faced while developing any embedded system, and it's one of applications and one simple example of any embedded system, and the block diagram about the embedded system, what it contains, what are the different units are present in the embedded system. So first question is, what is an embedded system? If I have to answer this question, I would say embedded system is nothing but a combination of an hardware and the software. So it's like an interface between a hardware units, like your input-output units and memory, and the software part. There are different challenges, like how to optimize the design, how to choose the controllers, what should be the hardware that are involved into design any embedded system. Then we have a different technologies, processor technologies, like what are the different types of processors, ICs technologies, and design technologies. Embedded system overview. Computing systems are everywhere. Like we have seen, even our computer is one of the computing systems. But can we call it as an embedded system or not? So if he says most of us think desktop computers, PCs, laptops, mainframe servers, we think them as a computing systems. But there are another types of computing systems which are very small, which we call them as a embedded system. So what is the difference between any PC or the embedded system? Like a PC, I would say, is a general computer which can be used to perform multiple tasks, where on the other side embedded system is designed or used only to perform one particular task. So it can perform one particular task repeatedly. So we have, you can see, embedded computing system, a computing system embedded within electronic device. So this computing system, it can be a part of a huge electronic device system also. It's hard to define nearly any computing system other than a desktop computer. So here we have given some statistics about like the number of units, embedded system units are produced versus the number of desktop units are produced yearly. So you can see that ratio is almost 100 times. So if I say if I'm producing a desktop unit, 1 unit per year, there is like 100 units of embedded systems are produced every year. So you can see here we have some examples of embedded systems. You can see a mobile, you can see even a car, like automatic control of your windows or even your windshield, and CD player, DVD players, even your washing machine, iPads, digital cameras, printers. These are some examples of embedded systems. So where hardware and software are combined together. So these are some characteristics of embedded system. As I said previously, embedded systems are designed to perform only one single task. So that is one of the main characteristics of any embedded system. It executes a single program repeatedly. Next, a feature of or a characteristics of embedded system is tightly constrained. That means they should be low cost, low power consumed, small and fast. There is no point in designing my washing machine or something a size of room, and it's consuming too much power that a consumer cannot even afford it. So, and there has to be a real fast. It's if I design a calculator which takes 1 hour to calculate just a simple calculation of addition of two numbers. There is no point in designing such that. So these are the one of the main characteristics. Then reactive and real time. So there should be a reactive to the change in the system environment. If my system environment changes, my system should be, or embedded system should be able to adapt to that environment. And there is always a real-time calculation involved in the embedded system. So here we have one small example about embedded system. So before explaining this, I would like to give you a very general block diagram of any embedded system. So main center part of any embedded system is a controller. It can have some sensor unit, which is interfaced with your controller. Sensor, again, as I said, embedded system is a interface, or a interface between your hardware and the software. Controller, it can be a microcontroller, microprocessor, or so which is a software driven, or any input. It's an input unit. Okay. And output can be it can be in terms of, again, controlling some parameter. It can be a display. So if I have to say, it is like yeah. So in general, embedded system is nothing but it has a three block. One is your inputs, another is your controller, which measure the inputs. I mean, it takes the inputs, reads the inputs, take the control action on that, and produce a result accordingly. So here we have an example for a digital camera. As you can see on the left hand side on the top, you have a CCD lens, then analog to digital converter, CCD preprocessors, pixel coprocessors, and digital to analog converter again. These are all hardwares, and it's inputs to the microcontroller. We have a JPEG codec in between a microcontroller multiplier. So memory unit, UART, it's for serial communication. It can be between external systems like your TVs, or it can be your laptops. ISA bus interface and LCD control. As I said, we have three main characteristics of any embedded system. One is it should be a single function, tightly constant, and reactive and real time. So if you see in this example, a digital camera performs only one task, that is your digital camera. It cannot be used as a washing machine or some other device. It only used for the capturing videos, or recording videos, or taking photos. So tightly constant, we see, right, how much power it consumes. There is only the low cost. It comes within your 5,000. You can even find it in 2,000 rupees. So, and it is very fast. You can find it as that processing speed is in milliseconds. And reactive and real time, that auto adjusting the flash based on the light intensity. You can set the picture quality or the brightness. So there are some certain design challenges while designing any embedded system that we have to look into. First is obvious design goal. So and construct an implementation with desired functionality. That means we should first know what is the functionality of our embedded system, right? So first we have to decide what it should perform. Then key design challenge, simultaneously optimize numerous design metrics. Design metrics, a measurable feature of system implementation. Optimizing design metrics is a key challenge. So common metrics is unit cost. Cost is one of the major challenge that we should keep it as low as possible depending on the customers and the application we are building. So unit cost, the monetary cost of manufacturing each copy of the system, including NRE cost. NRE is non-recurring engineering cost. It is actually the one-time monetary cost of designing the system. The size, it should be very small. That is again the characteristics of any embedded system. It should be low power, small in size, right? Physical space required by the system. So we have to design a layout. Power, the amount of power is consumed by the embedded system. It should not be very high. So, and the one more challenge is the weight. It should not be very bulky. Flexibility, the ability to change the functionality of the system without incurring heavy NRE costs. So this is like if you have to change any functionality in the embedded system, we don't have to go, we should not go in redesigning it again. So that will again increase the engineering cost. So our embedded system should be flexible enough to for any changes. If I have designed a version 1 and I want to upgrade it to version 2, we should be able to change that functionality or add some functionality into the system without changing the actual design of the particular system. So common matrices continues. So it's time to prototype, the time needed to build a working version of the system. So this also should be very limited. It should not be tracked too much. Like if I am designing a system which is required by the customer today or maybe after 1 month or 2 months, but my building, if I take a more time to build that working version for like 4 months, 5 months, there is no use. So that should be time before, time to market, the time required to develop a system to the point that it can be released and sold to the customer. So this is also should be defined. See, once we have designed an embedded system, it should be released when the customer is needed. If we release it to the market when the already customer are not don't want that technology already, like this is okay, this is I have better one. So looking into the market, we have to release our products or the embedded system on time. Maintainability, the ability to modify the system after its initial release. So it should be we should be able to maintain it and modify it even release, after first release also. Correctness, safety, many more. See, correctness and safety are very much important to any embedded system when it comes in the application like medical or your aerospace. So there the safety for the patient in medical devices is very much important. The correctness in the aerospace or even in the military, the application is very much required. we have an example here about a smart system. So this is a smart system is a it's actually a automated light control system, or I can say it's a smart light control system. So here we have the requirement that switch on bulb when there is a human. So these are the requirement analysis for that embedded system what we have designed. It's a automatic light control. Suppose there is a human present in that sensor range, it should detect it and switch on the bulb. So design of dip switches for different timer values. That means a user should be able to decide how much time he wants bulb to be on if there is a human is detected. So we have a basic block diagram here. PIS sensor. This is a sensor which is used to detect the human movement in the area or in the room. A microcontroller, and a track circuit. Microcontroller, there are is one of the control unit of the embedded system. There are various varieties of microcontrollers are present in the market. For example, you have 8051 architecture, PIC architecture, ARM architecture. So based on the application, we can decide what type of microcontrollers we need. So whether we need a 8-bit microcontroller or 16-bit microcontroller or 30-bit 2-bit microcontroller, what should be the memory size, how many inputs, outputs are required, what are the different peripherals are required in my application, so what should be the size of the controller. So all those things are very much important while designing any embedded system. So for example, let's consider this example only smart system. Here we have one PIR sensors. That means I need one input pin to connect to my microcontroller. So my microcontroller should have at least one input pin. Okay, it's again connecting to 4 dip switches. That means it requires again 4 more IO pins. It has one control to the bulb, so that means I should have one output pin. So at least if I consider this system, my controller should have at least 6 IOs plus VS, VCC, and that also is very important while choosing the microcontroller, is how much power the microcontroller is consuming. So mostly, if you consider PIC architecture, mostly microcontrollers they'll be consuming in nanoamps. The current that is consumed by PIC microcontrollers is in nanoamps. Even in ARMs also it can go up to nanoamps, microamps. If you consider a 8051 architecture, the current consumption for microcontroller it's in milliamps. So based on our application, based on what power consumption we want for our application, we can even choose the microcontroller. Based on next factor is cost. If we can take a ARM, which is a 32-bit microcontroller, the cost will be maybe high. But if I am designing this my smart system, there I require only a very small microcontroller, which is within say I would say 30-40 rupees. And even my 8051 architecture will do the work. What I can do with the ARM also, where ARM will cost me around 200, maybe 400 rupees. So this is one of the important aspects in choosing microcontrollers. So we have a microprocessors also. So there is what is the difference in the microprocessors and microcontroller? That also matters. Like why we can't go for the microprocessors in that whether I should choose a microprocessor or microcontroller for my application. So one of the basic difference in the microprocessors and the microcontroller is microprocessor does not have any IO units. Like it does not have your input outputs, your UART, everything. It is IO ports. Yeah. So where the microcontroller have all the IO peripherals or IO ports, you can say. So See, this PIR sensor is a passive infrared sensor which is used to actually detect the radiation from the human body. So based on the radiation, like it receives, it will switch on and switch off, which will give a pulse of somewhere around 15 seconds. So it will give an on pulse of 15 seconds and then it will be off. So at this point, the point, I'll say it's a T1. T1 is the point where the PIR sensor detects any human. It goes on and it will remain on for the 15 seconds. This is the PIR sensor property here. And after 15 seconds, it will be off if there is no human movement. If there is a human movement, it will continue to be on. So this triac circuit is used. This triac circuit is used to glow the bulb. So it receives the input from the microcontroller. Based on that, it will trigger the triac, and 230 volts will be given to the bulb. Yeah. So here we have the circuit diagram. You can see PIR sensor, and that input is given to the. So this is our PIR sensor. Okay. We have a PIR sensor. It's the input of the PIR sensor is given to the microcontroller. From microcontroller, we have used a transistor to increase the current. For the optocoupler, this is a triac, and from triac, once the triac is triggered, it will connect 230 volts to the bulb. So here you can see a PIR. Pin, which is taken as the output port. Trigger the triac, and once the triac is triggered, it will connect 230 volts to bulb directly. So you can see this is the VCC connection, pin number. This is the reset connection for the microcontroller. Microcontroller, it has a reset button, and pin number 40 is a VCC, and pin number 20 is ground. So here we have used Atmel IC that is 8051 architecture based. It's an 8-bit microcontroller, and it's a 40-pin IC. So even in the same architecture, we can find an ICs with different pins based on they may have different features. Like if I choose a PIC microcontroller, it supports ADCs. Even it has some DAC also, that digital to analog converters. They have USB supports, UART, SPI, PCI, I2C modules, even PWM channels, but they all differ depending on the pin configuration or depending on the series of the that particular controller. So here we have a PIR sensor which has 3 terminals, VCC, ground, and yellow is output. VCC is connected to the 5 volt. So yellow PIR output is connected to the base of the transistor, and to drive the load, external load as current is less, emitter is connected to the microcontroller input, that is P2.0 pin. So you can see here, this one. This is a BC547. Base is connected to the PIR sensor. Then emitter is connected to the P2.0 pin of the microcontroller. So this is another example of microcontroller, that is P89V51RD2. It's again a 8051 architecture based IC. It's an 8-bit microcontroller with the 64-bit 64 KB memory size. So it's a 40-pin IC. So you can see there are 4 ports: port P1, P2, P3, and P0. P0 is externally pulled up port, where other 3. So this is also important, like how many IOs are present in my microcontroller while choosing for your particular application. We have used only 11.0592 megahertz. It has a prescaler of 12, or it can be a 6 also, based on the manufacturer. So prescaler is nothing but it decides the actual frequency that is microcontroller operating. Suppose, for example, if I have my crystal oscillator is 11.0592 megahertz, and my, if I say my prescaler is 12, then the actual frequency that the microcontroller will be getting is, that is nothing but the size of one machine cycle, that will be f oscillator by 12. So my actual frequency will be just 921 kilohertz, with, and if I calculate the time period, it will be 1 by f oscillator. So that is, if it says, it will be around 1.085 microseconds. So if you want, like if I as I said, based on the application, if you want high operating speed, we can choose a microcontroller which can be operating at higher frequency. So for example, if I take a PRIC architecture, and the microcontroller is operating as at 20 megahertz, but there the prescaler value is only 4. So it's still the crystal oscillator frequency is less compared to 8051, but the prescaler value also is reduced. So actually my controller will be getting around 4 megahertz frequency. So yeah, and if we consider AVR, AVR they have a prescaler of 1. So this is the schematic diagram. It's a pin detail diagram for the opto-isolator, that is nothing but tracks. Okay, so anode, cathode, we have anode and cathode here, zero crossing circuit, and the output terminals, main terminal. So this is the actual output of the microcontroller or the smart system. Here the red waveform represents the PIR, and blue line represents the microcontroller output. So as I said previously, that PIR, once it is detected, any human detected, it remains on for 15 to 20 seconds. So this system is this data is captured only for the 60 seconds program. Like if whenever the human is detected, my bulb will be on only for the 60 seconds. So you can see at the point here, as soon as my human is detected, PIR detects the human, my microcontroller output also goes high. So it remains high as long as PIR is on. Once the PIR is off, it still remains on for next 60 seconds. So it's this time period we can vary based on the dip switches. So that dip switches what we have given here, it can go. We can design this microcontroller to go up to even hours also, the time delay. Okay, thank you. If you have any doubts, please you can post me. Thanks.